First, we just want to introduce ourselves. My name is Tamar Shinar. I'm an assistant professor at UC Riverside. And this is the first time Adam and I are doing this course, and we're excited to talk to you about physics-based animation today. So now I'll let Adam introduce himself.
Hi, I'm Adam Bartel. I'm at the University of Maryland, Baltimore County. I'm also on the SIGGRAPH Executive Committee, so if you have feedback on the conference or just SIGGRAPH in general, feel free to get in touch. Is that better? Yeah. Is that good? Okay. Also, if you have feedback on this course, because this is the first time we were doing it and we might do it again, please do drop us a line and let us know. Good or bad, or, Okay, so let's jump right in, and we'll start with a simple system of particle dynamics. And we'll jump right in and consider the problem of tracing a particle through a velocity field. So here's a velocity field, and here's a particle, and you can imagine that the particle might trace a path something like this through the velocity field, and if we have another particle, it would trace a different path through that velocity field. We can express this mathematically as what we call an initial value problem. Here we have xp's position at time 0 is just a given. It's x sub 0. And then we have the change in position with respect to time is going to be equal to this velocity, which can be evaluated at any point xp at any time t. And so since we're looking at change, another word for change, the change in position, another word for change is difference. And that means we call this a differential equation. It happens to be an ordinary differential equation, which distinguishes it from partial differential equations, which we'll see later. I'm unaware of any extraordinary or unordinary differential equations. And this is also a first-order ordinary differential equation because we only have a single derivative with respect to time. One reason that we're considering this problem is that it's really simple. It's also very, very powerful. By specifying time-varying and position-varying velocity fields, you can actually create really interesting particle dynamics and animations. And in fact, this problem does come up a lot in practice, even in more complicated systems. You end up tracing particles through some velocity field. And it's also really instructive. We can actually learn a lot just by looking at this very simple system. So how would we solve this system with a computer? And the simplest method is attributed to Euler's method. We can get intuition into Euler's method by looking at the definition of a derivative. So you probably remember this from your first calculus class. So the derivative of xp with respect to time is the limit as epsilon goes to 0 of the difference between xp at t plus epsilon minus the xp at time t divided by epsilon. And what we do for Euler's method is we take epsilon and just replace it with a finite amount of time, delta t. And so that gives us an approximation to the derivative, where we have a finite time step. We can take that approximation and we can replace the left-hand side of our differential equation and then rearrange terms a little bit, and we get an update rule for the position. And so we have that xp at t plus delta t is just going to be xp from the previous time step plus our time step delta t times the velocity. Oh, I circled those. So at this point I'll point out the big trade-off that we have in all of scientific computing and physics-based animation. And that's that as delta t decreases, the approximation we have to the derivative gets better. So the solution that we get, the animation that we get, gets better in an accuracy sense and also generally in a quality sense. But what we pay is that there's increased computational cost. So as a general rule, you can always get a better animation just by paying more computation time. So let's consider another problem. In the real world, we don't trace particles through velocity fields. We actually have F equals ma, Newton's second law. This results in another initial value problem where we have the same initial conditions as before, but now we have a second derivative of the position with respect to time is equal to some force function divided by the mass of the particle. This is a second order ordinary differential equation because we're taking a second derivative with respect to time. we often, what we'll do is we'll express the second-order differential equation as a system of coupled first-order differential equations. And so you can see that here we have now two equations, one for position and one for velocity, but the one for position now depends on the velocity. We can use Euler's method again to solve this. So we first update our velocities using an Euler step where we take delta t times the forcing function divided by the mass of the particle, and then we update the position based on this new velocity that we have. And this is generally referred to as symplectic Euler, and if you're going to use an Euler integrator, this is the one to use. We can look at what code for this would look like. So here we have a structure for our particle class. It's relatively simple. We have a mass, a position, a velocity, and then a force accumulator. We'll loop over all of the particles, zeroing out their force accumulators. Then we'll loop over all the forces, and for each particle that force touches, we'll update its force accumulator. And then we'll loop over all the particles again, updating them with an Euler step. So we just update the velocity by the time step times the force divided by the mass, and we update the position by the time step times the velocity. At this point, I'd encourage you, after the course or during the break, to go check out Carl Sims' Particle Dreams. I would play it here, but we don't have rights to it, and we're recording this to put on the internet later. So now we'll add springs to our particle system. If you studied springs in some physics course, you probably saw the spring, the idealized spring expressed with F equals, the force is equal to minus kd. This is a zero-length spring that's attached to the origin. We'll actually replace the notation with the notation we've been using, so we'll say that Fp, the force on particle P, is going to be minus k times the position of particle P. What if we want something that's a non-zero rest length? Well, what we'll first do is we won't actually change the formula, but we'll rewrite it, separating out the magnitude of the spring force and the direction of the spring force. So the magnitude sort of in that parentheses there, and then the direction is xp divided by the magnitude of xp. And then we can just subtract off the rest length when we're computing the magnitude of the force. It turns out that this isn't the best way to actually express a spring force, and it's much better to define a strain metric where we take xp divided by the rest length and subtract 1. So if xp is equal to the rest length, this gives us a zero strain. What's nice about strain metrics, and we'll see this a little bit later in the course, is that they're independent of, they're dimensionless. They're independent of the scale of your system, and this makes k a material parameter. So if you have some simulation mesh and you have some k associated with it, and then you refine that simulation mesh, if you're using a strain metric, then you don't have to change your material properties. They are independent of the resolution of the mesh. If you look at when we had the rest length actually showing up in our formula, that puts some meters in there. And that means that our k then depends on meters, and it makes things more complicated. Okay, so we substitute in this strain metric, and we have a nice non-zero rest length spring. The next thing we'd like to do is to add an arbitrary connection point. So instead of being connected to the origin, we want to connect to an arbitrary point, xq. And to do that, we replace the magnitude of xp with the magnitude of the vector from xp to xq, and then we change the direction from just the xp to being the direction from xp to xq. And notice that we folded the minus sign into the direction there. And then, of course, to obey Newton's third law of motion, we need equal and opposite forces, and so the force on particle q will be equal to the negative of the force on particle p. Finally, we'll add damping to our spring, because damping models internal friction, and without it, things don't look very realistic. Here's our damping term, and I'll go over what's in here. So this is the relative velocity between the particles, scaled by our rest length. This is the spring direction, and so we're taking the dot product of the difference between our velocities with the direction of the spring. So we're not going to damp any velocity that's not in the direction of the spring by taking that dot product, and that just gives us the magnitude, and it's still going to be in the same direction as the spring. And putting this all together, we get a formula that takes up the whole slide, but each individual component of that formula is relatively simple to understand, and writing this, computing all of this takes just a few lines of code, as you can see here. So just like before, we have a loop over all of the particles, updating the forces. setting the forces to 0, and then for each spring, we loop over all the springs. We compute the direction for our spring, then we compute the length of our spring, then we compute the difference in our velocities, and that's all we need to compute the forces. So we have a parameter for the spring constant, we have a parameter for the damping constant, and we have all of the things that we saw in the previous formulas. Then we update the force accumulators for our particles at I and j, and then we exit that loop and go to another loop where we're loop over all of the particles, updating their velocities and positions just like before. And so at this point, I'll show a demo of, I'll show the actual code first. So this is an actual program. We'll put this on the web with our course notes and our slides soon after today. We have our main program. Let's see. Yeah, there's parameters, there's objects. We read an input file. We set our time to 0, start at the beginning of time. We set our frame number to 0. By setting frame time to -1, we make sure to drop a frame at the very beginning of our simulation. Then we run until our time is up, and we loop over everything. We look and see if we need to write a frame. This is code that writes a frame. It's nothing too interesting. And then we can take a time step. And so we loop over all of our objects. And you can see that we set all of our force accumulators to 0. In this case, we actually add gravity just to the z coordinate. Then we loop over all of our springs. And this is exactly the same code that I put on in the slide. And we loop over all of our particles, updating and doing our time integration. And then in this code, we'll actually collide with the ground. And when we do collide with the ground, which we just set as 0, we'll set our position to 0 and we'll set our velocity to 0. So we'll treat the ground as a constraint on our positions and velocities. And then we update our time and we decrease the frame time, so we drop a frame at the next time step. And this simulation loop is typical of all physics-based animations. You take time steps marching along, and when it's time to write a frame, you write a frame, and then you continue marching along. And then here's the input parameters that we have for our system. So there's the time step, there's the total time, so this will be a 2-second animation. We can specify a stiffness for all our springs, and we specify a damping constant for all of our springs, and then an input file name, and then a way to write out files. And so I can run this, and we get 60 frames, and then this is Houdini. Uh-oh. I can't see. Oh, no. It rescaled my screen, and now I can't. Oh, here it is. Well, so you can sort of see it's bouncing on the ground. I wonder if I can move this time bar out of the way. But you can sort of see it falls to the ground and bounces. Not the most exciting physics-based animation you've ever seen, but it's a relatively simple system. We can go back to our code and change the stiffness, make it a stiffer material. And if we do that and run again, the system actually blows up. We had too large a stiffness for the time step we were taking, and you can see in this first frame that it goes unstable. And we'll be talking later about what all that means when we talk about implicit integration. So we'll reduce the time step, and that'll make things more stable. And now we'll run again, and we're stable, but we're a more stiff system. And you can see we bounce a little higher. Okay, and this introduction clearly took less time than I thought it would. So if there's questions on the particle dynamics part, I'd be happy to answer them, and then we'll move on to mathematical models. There's 2 mics in the middle of the room if anybody has any questions. Nope? Oh, okay. So we take the, actually, so that's exactly what the dot product does. Let's see. So we have a dot product between the difference in velocities with the spring direction. And so, yeah. Go ahead.
What was the configuration of the springs in that model? Where was it every particle or every corner connected to every other corner? And how does that configuration affect the solution?
Yeah, it affects it a lot. So spatial discretizations matter quite a bit. Let me play this again. To the extent that you can see the faces that are showing up there, so this is actually a volumetric mesh. I'm only rendering the visible faces. To the extent that you can sort of see the scale of the faces there, those are the actual springs. So what I did was to take this object and run a meshing program on it and generate a volumetric tetrahedral mesh, and then for every edge in that tetrahedral mesh, we created a spring. If you were to create a finer spring network, you would get different behavior because you've changed your spatial discretization. But because we use that strain metric, that behavior will converge under refinement. So as you refine further and further and further, you'll converge to some behavior. Yeah. Any other questions?
Yeah. I was expecting to see actually particles in your example, but I see a mesh. So every vertex represents like a particle position?
Yes, exactly. So, and there may be even some particles that you can't see because they're inside of the mesh. If I was more familiar with Houdini, I could show you the actual vertices of the mesh, or the particles, but I'm not. If you're curious, I do have, let's see. So here's the 60th time step. Here's all of the springs that are on the surface. And then here's all of the particles that were used to, as the vertices or of the spring network, the particles. This one's the prettiest, I think. Any other questions? Okay, well, thanks. At this point, I'll turn it over to Tamar, who will begin talking about mathematical models.
All right. Okay, so much of what we're going to do in physics-based animation is going to be based on the laws of classical mechanics as formulated by Isaac Newton. He published these laws in the Principia in 1687. And among other things in that work, there's his 3 laws of motion. Newton's first law, which is also called the law of inertia. Newton's second law, which is F equals ma. Newton's third law, or the law of action and reaction. And these laws treat the body as a whole, or equivalently kind of as an idealized point mass, or a particle with a mass. Okay, so Newton's first law says that a body persists at rest or in uniform motion in a straight line unless acted upon by a force, also called the law of inertia. And so if a body is stationary, unless it's acted upon by a force, it's going to stay stationary. If it's moving at some constant velocity, if there's no force acting on it, it will continue to move at some constant velocity. And Aristotle actually believed otherwise and promoted a different worldview where for an object to stay in motion, a force was actually required. And you can imagine that's kind of consistent with our experience because if we see objects in motion, we notice that they eventually seem to come to rest. But now we understand better that that's actually due to effects like friction or air resistance, another form of friction, that counteract the motion of the object to give it to decelerate it. So Newton published this law. And actually, I believe it was, unlike the other laws, it was actually not originally developed by Newton, but a few decades prior by Descartes. Okay, so Newton's second law tells us more about how a body accelerates. In particular, it says that the rate of change of momentum of a body is directly proportional to the force applied to the body. So, see if my pointer works here. Yeah, okay. Over here we have the rate of change of momentum, and we're more used to seeing this now. If the mass is constant, we can move that derivative in to just apply to the velocity, and then that becomes an acceleration. So we're used to seeing this law in the form F equals ma. And so for some constant force, we'll get an acceleration with they'll be proportional, and the constant of proportionality is the mass of the object. So for a given force, if the mass is smaller, there'll be a larger acceleration. If the mass is larger, there'll be a smaller acceleration. That's why in a collision, let's say between two vehicles, the more massive one, they'll both receive an equal force from each other in magnitude, but the more massive vehicle would accelerate less, whereas the less massive vehicle will experience a higher acceleration. So for safety, it's good to be in the massive car. So this is really the basis for evolving a system of interacting particles or interacting bodies. And it's a differential equation. It's a time evolution equation. So it's going to let us predict the future based on some current state. Okay, and as Adam showed us, it leads to a system of first-order ordinary differential equations. X dot, the time rate. Here we're using the dot notation for time derivative, very common. And so X dot is the time rate of change of position, it's the velocity. And V dot is the time rate of change of velocity, the acceleration. And by Newton's second law, that's 1 over mass times the force. So the way that Newton's second law is applied is that we have some body or particle, like what's shown here in blue, and we characterize all of the forces acting on the particle. So when using Newton's law, we have to have a model of all forces acting on the particle to get the right dynamics. And in this example, we have 3 different forces acting on the particle: a gravitational force pointing straight down, Fg, a spring force, and some other force, external force, Fe. And we sum those all up. That's the net force acting on the particle, and equate that with the inertial term, ma. Okay, and the same is for a system of particles. That was a single one. If we throw in a bunch of particles, for each particle, we characterize all the forces acting on it, as Adam also showed us with the force accumulator, and then we integrate forward in time. Okay. So Newton's third law tells us more about how two interacting bodies exert forces on each other. In particular, they exert a force on each other that's equal in magnitude and opposite in direction. So if body 1 applies a force F to body 2, then body 2 necessarily applies a force minus F to body 1. Here's some examples. Our spring force. These particles are interacting through a spring, and if we stretch that spring, the spring will try to exert a restoring force to try to bring them back to their rest length. The restoring force will be a pair of forces, and they'll be equal in magnitude and opposite in direction. Another example where we use Newton's law, third law, is in a collision of two bodies or two particles. So in this collision, there's going to be some force at the time of collision, or an impulse, that will act on equal magnitude, opposite direction on both bodies to prevent interpenetration of the bodies. And same here, we have a particle resting on the ground. The force of gravity is acting on the particle, minus mg. And so the particle is pushing on the ground with minus mg. And now the ground will push back up with mg, and so that these will cancel each other, resulting in a net force of 0 and an acceleration of 0 for this particle. So that was Newton's laws, a very brief introduction to it. And another formulation of classical mechanics that's used a lot in physics-based animation is called variational mechanics, developed after Newton's time by Euler, Lagrange, Hamilton, and others. And Newton's laws are based on vectors in Cartesian space. So kind of like what we're used to thinking in terms of Cartesian space. In Newton's laws, we formulate all the forces based on vectors and alternatively, in the variational approach, we derive the equations of motion from what are called principles of least action. So we actually define some action and minimize it, and it gives us the equations of motion similar to F equals ma. The difference is that in a variational approach, we don't have to use the Cartesian coordinates. We can actually use any set of coordinates. And the power of that approach is that we can actually use coordinates that take into account constraints. And we'll come back to talk about that more near the end of the course today. So we can use a special set of coordinates that respect constraints and allow us to not explicitly characterize all the forces in the system. Okay. So in addition to Newton's laws, other important physical principles that we use a lot in physics-based animation are conservation laws. So if a quantity is conserved, this tells us that that quantity cannot be created or destroyed. So examples of this are conservation of mass, conservation of linear momentum, conservation of angular momentum, and conservation of energy. Conservation of mass and energy are said to be inexact because really there's a mass-energy equivalence, but we don't really worry about that in physics animation too much because we're in a regime where we can assume that they're conserved. Okay. So why are these important in physics-based animation? Well, the first reason is that they're actually used to derive evolution equations for how materials evolve, like our fluids and soft bodies, elastic solids. And another reason that it's very, very important to be aware of the conservation laws is because we're starting with a bunch of continuous math equations, Newton's second law, other continuous PDEs we'll see. But we're going to compute these numerically. When we go from a continuous equation to a discrete set of equations that we can actually compute, there's a big range of choices we can make. And these conservation laws often inform the choices we make in choosing our discrete set of equations. So a lot of times it's beneficial for the discrete equations to also have numerical conservation properties, to numerically conserve mass, to numerically conserve momentum, and to numerically conserve energy. And this is not necessarily easy to do, and so lots of methods are used that don't have these conservation properties but still converge to the exact solutions. But there are a lot of benefits to it. So when we're designing numerical methods for physics-based animation, it's important to keep these conservation laws in mind. So conservation of mass, it cannot be created or destroyed. We'll see that we use a lot of particle-based methods. A particle will have a mass attributed to it, and so conservation of mass is pretty easy in particle-based methods because as long as we don't create or destroy particles, then our mass is going to be well conserved. Or if we do create or destroy particles, we just have to do it carefully so that overall mass is conserved. We also use the grid-based methods, and these sometimes do have issues with proper mass conservation. For example, when we do fluid simulation, in some fluid simulation approaches, we can observe some loss of mass that can be visually disturbing. So now for conservation of momentum, if we look at Newton's second law, if there's no forces acting on the body, then that means the right-hand side here, our F is 0. And so the time rate of change of momentum is going to be constant. So their momentum is conserved. And in the same sense, if there's no net torque on the body, and we'll talk a little bit more about torque, the angular momentum of the body will also be conserved. So Newton's third law gives us conservation of momentum because if we have forces acting between two interacting particles and they're equal in magnitude and opposite in direction, then if we just consider those forces here, they're going to cancel each other. And so if we look at the system as a whole, for the whole, all of our whole system, here are two particles. The total momentum, we're going to have one particle acting on the other with F1 and the other one acting on the first with minus F1. Those will cancel, and so that also gives us conservation of momentum. And very similarly, that Newton's third law gives us conservation of angular momentum. So here, L represents the angular momentum, and these two particles are interacting as before. Now, the angular momentum is this moment, or this R cross F. That's the angular momentum associated with the force F1, R1 cross F. And the angular momentum associated with minus F1 is going to be R2 cross minus F1. So if we just pull out the F1, we have R1 minus R2 cross F1, and that's going to be 0 as long as F1 is in the direction of the line connecting the two particles. So that cross product is going to be 0 because the sign of the angle between those vectors is 0. Okay. And the same is going to be true for a system of interacting particles. As long they're respecting Newton's third law, so they're interacting through pairs of forces that are equal in magnitude, opposite in direction. All right. So conservation of energy. Here's a simple illustration of how we usually encounter this in physics. We have some body initially at rest at some height h0. So initially, all of its energy is potential energy, gravitational potential energy. And an approximation to that is mg times h0, the initial height of the body. So by conservation of energy, if we release this body and it falls, that potential energy gets converted into kinetic energy. And we have the total energy being the sum of kinetic energy and potential energy, and the requirement of conservation of energy says that that total always has to be equal to the initial amount of energy. So that can be used, for example, to calculate the speed when the object actually hits the ground. If we just plug in h of t is 0, we can figure out that speed. So in terms of numerical methods, again, different numerical schemes have different energy conservation properties. And in many schemes, this can be an issue if the energy grows or decays non-physically. If it grows non-physically, well, if it grows too much, we'll see an instability, or what we like to call the simulation will blow up. And what we see is that very quickly, this happens in a matter, once this phenomena sets in, it happens very quickly. And what you will see is either sort of oscillations that are growing significantly and quickly going to infinity, so we start getting infs and nans from our program. On the other side, flip side of things, if energy is being non-physically damped, we'll see that the motion of whatever system we're simulating looks kind of not lively enough. It looks too damped. So keeping in mind conservation of energy is important in our numerical schemes. The last thing I want to say about conservation laws is that they're used to derive the evolution equations for continua. So we've been talking about particles, but when we're simulating something like fluid or some soft material, then usually we use a continuum view of things. That is that we're on a macroscopic scale that's large enough that we don't have to consider individual particles, so our mathematical models assumes that this is a continuous material. Now, to derive a conservation law for the continuum, what's usually done is we draw some arbitrary area here, and we've labeled this omega, and the boundary of this area is d omega. And for example, if we look at conservation of mass for this, so the total mass inside this area is the integral of the density. It's a volume integral. It's on the left. And conservation of mass tells us that that can only change in time if stuff flows in through the boundary or flows out through the boundary. So mass is not going to get created or destroyed, so it's not going to spontaneously arise or disappear inside that volume. It's only going to change if stuff comes in through the boundary or leaves through the boundary. And that's what this first equation expresses, that the time rate of change of the total mass is the flux through the boundary. So now we apply a couple calculus theorems and things that we will see a lot. And so I'm not in this course, but if you do physics-based animation, you'll see them a lot. So one of them is divergence theorem. That's going to convert the surface integral over here into a volume integral. The other thing is bringing this time derivative under the integral, which we can do simply when this region is fixed, as it is in our case. And so those two things we rearrange a little bit, and we get what's called this continuity equation. And this is a partial differential equation that describes how the density in the system should evolve to respect conservation of mass. A similar type of equation is also derived for conservation of momentum, for example, in fluids. And in general, these conservation laws look like this. There's some conserved quantity u, and the partial derivative of u with respect to time is going to be equal to the negative of the divergence of the flux, or putting them on their same side here, plus divergence of a flux function. Okay. Now I wrote that these are local conservation laws. So that control volume we chose, that omega, was arbitrary. I can make it as big as I want, as small as I want, put it anywhere I want. It still has to hold everywhere. And so we can't create mass over in one spot and destroy it over here and still respect local conservation. Maybe on a globally we would be conserving mass, but locally we would not, and that would be non-physical. Okay. So what I want to talk to you now about are rigid bodies. So we saw mass spring systems. And in many cases in physics-based animation, we're interested in simulating things where deformation is negligible. So it's sort of examples all around us. This podium, if we were simulating it, even if I was going to knock it over or something like that, we probably wouldn't be interested in seeing its actual deformation. You might be able to see it if you look at very high-speed camera footage, but generally, unless it breaks, we're not too interested in its deformation. And if we used our mass spring system, we'd have to capture this by making the springs very, very stiff. Now, if you have, first of all, that's quite inefficient. If you have very stiff springs, that forces you to take small time steps in your simulation or to switch to implicit integration, which you may or may not want to do. It also means that we're going to have a lot of particles describing our object. So in a rigid body idealization, and this is an idealization, the stiff springs are thought of conceptually as actual constraints. So in a rigid body is something where every point on the body stays a fixed distance from the other points. That's the rigid body idealization. And now, to simulate rigid bodies, we actually go a step further and we replace this model of a bunch of particles with 6 degrees of freedom. So let me explain that a bit. Degree of freedom is the number of degrees of freedom are the number of parameters that you need to describe the configuration of something. So a particle in 3-dimensional space has 3 degrees of freedom because its position could be described with x, y, and z. So if we used particles to model our rigid bodies, let's say we used n particles, we would have 3n degrees of freedom. But it turns out actually that to describe a rigid body, you don't need that many degrees of freedom. In fact, in 3 dimensions, you only need 6 degrees of freedom. And this is very widely used because it's so efficient. So you take 3 times n and replace it with just 6. So what are these 6 degrees of freedom? Just like a particle, we have 3 for position. But now also a rigid body has spatial extent. And so we have another 3 degrees of freedom to describe its orientation. And that's labeled here as R for a rotation matrix. So if we look, for example, at this object here, which could be modeled as rigid, 3 numbers will be used to say where it is in space. And then we have 3 more numbers for its orientation. So imagine a sphere around this. And if I point it to different points on the sphere, how many numbers is that? Well, a sphere is 2 because we have latitude and longitude. So that's 2 more degrees of freedom for where it's pointing on the sphere. And then the third one comes from the rotation about its own axis. So that's our third one. That's just one way to parameterize orientation, and there are infinitely many ways. Now, I wrote R here for rotation matrix. In practice, it's very common to use what are called quaternions to represent orientations and rotations in physics-based animation, but we won't talk more about those today. Okay, for rigid bodies, we're going back to this particle view of things just because it's easier to derive certain quantities like this. So even though we're going to use this 6 degree of freedom representation, just to talk about certain quantities, we'll think of it as made up of a bunch of particles with different masses at each particle. So the center of mass of the body is the mass-weighted average of all the positions of the particles. So it's the sum over each particle of the mass of the particle times its position divided by the total mass. And the center of mass, if a body is uniform, if its density is uniform, that center of mass will be in the geometric center. If the body is not uniform, that center of mass will tend to where the body is heavier. When we talk about rigid bodies, we introduce another space. So we don't just have our regular 3-dimensional space, we have something called object space. Object space is a space that's fixed to the body, and it's very common and very convenient to put the origin of object space at the center of mass of the body. So from now on, we'll assume it's at its center of mass. With object space, we can describe the position of any point on the body. For example, one is illustrated here at position R0. So as this object translates and rotates, it'll move in world space. And that point that's at R0 in object space is going to be at R, which is a function of time, as the body moves around and rotates. Now we're going to talk a little bit about the implications of having this 6 degrees of freedom. So for just a particle, we have its velocity. For a rigid body, that becomes its linear velocity. And so just like for a particle, it's the time rate of change of its position. But for a rigid body, that is the position of the origin of our object space, in our case, the center of mass. Now, for a rigid body, since we have that 6 degrees of freedom, we need 3 more numbers to describe its velocity. This is really what we call a generalized velocity. So the 3 other numbers are the angular component of the velocity. This is a 3-dimensional vector in 3D, and it points in the direction about which the body is instantaneously rotating. And the magnitude of this vector is the speed of rotation. about that axis. Okay. So the body itself has this linear and angular velocity and a position and orientation. If we want to know the position or velocity of any point on the body, these are the formulas that give it to tell us that. So that particle at r0, as the body moves and rotates, it's going to be located at the rotated r0, which is r times r0 plus x, wherever that body is in space. So you take to find the position of this point on the body, we first rotate it to be in its current orientation, translate it, and then we can figure out where the point on the body is. And if we want to know the velocity of some point on the body, so every point on the body could have, the different points on the body could have different velocities, right? So if we want to know the velocity of a particular point on the body, it's going to be the time rate of change of the position. And that, it turns out, is equal to the linear velocity plus omega, the angular velocity, cross r, the vector that points from the origin in object space to, or sorry, from the origin of the body fixed coordinates to the position. Okay. So we also have notions of both linear and angular momentum for the rigid body. The linear momentum, if we put the center of mass as the origin in object space, has a very nice simple form, and that it just looks like the linear momentum of a particle. It's just mass times velocity. But the way we can get it is by summing up the linear momentum of all the constituent particles. And the angular momentum, if we sum up the angular momentum of each constituent particle of this body, and after we do a bunch of rearranging and assuming that the center of mass is the origin, the angular momentum takes this form. It's a matrix I times the angular velocity. So it's kind of analogous to the linear momentum, which is mass times linear velocity. Angular momentum is I, the inertia tensor, times the angular velocity. And the inertia tensor is to angular momentum kind of what mass is to the linear momentum. If we look at what this inertia tensor is this is the expression for it, but what I sort of want you to know about it at this point is just that the inertia tensor describes how mass is spatially distributed through a body. And that affects that body's motion. So the simplest or very common example is the ice skater. The ice skater doing a spin on the ice has a certain, if her arms are out, she has a certain inertia tensor. Now, angular momentum is going to be conserved unless some force is acting on her. So let's assume that there's zero friction with the ice. So she's spinning around. Angular momentum is conserved. And angular momentum is equal to I omega. So she has a certain angular velocity. Now, as she pulls her arms in, what's changing is I, the inertia tensor, the distribution of mass. So in fact, what's happening is that these R terms, the spatial extent associated with the mass, are getting smaller. And for conservation of angular momentum, omega will grow commensurately. So as she pulls her arms in, angular momentum is actually being conserved, but she's speeding up. Okay. So this is just reiterating that, which is when it comes to rigid bodies, the angular components sort of take a lot of thinking about. They're not quite that intuitive like the linear components. For the linear component, if there's no net force, linear momentum will be constant and velocity will be linear velocity will be constant. But for the angular component, if there's no net torque, angular momentum will be constant, but angular velocity won't necessarily be constant. So it's a little bit, you could argue whether it's intuitive or not. There's some cases where we're used to seeing that, but definitely thinking about rotations is a little harder than about linear components. Okay, so this is a summary of what Newton's second law for rigid bodies looks like. Rather than just time rate of change of linear velocity, we have the time rate of change of both the linear and angular velocity. And the linear part is the same as for particles. Time rate of change of linear momentum is the force. The angular part, on the right-hand side, we have the torque. Okay. Pass it over to Adam now.
Okay. I didn't expect this all to show up at once, but okay. So we start with F equals ma, Newton's second law of motion, and we want to add to that the elasticity and the damping terms. And so we do that by adding this function k of x minus u, and that's our elasticity, and then we have a damping term that's dependent on the velocities. If you look in the literature, you'll often see this system expressed in terms of displacements, and that's typical because it cleans up the x minus u, which is just a little bit inconvenient. I want to talk a little, so let me, okay, so here we just have F equals ma. This is a generalization to a large system. Here's our damping term, which is dependent on the velocities, and then we have our elastic forces, which are dependent on positions. I want to talk a little bit more about the matrix K. This is a generalization of spring stiffness. Once we discretize our system, it will end up being a matrix. It's typically called the stiffness matrix, just like we call K the stiffness constant for a single spring. It has a very, very special structure. It's a sparse matrix. There's only connections. The only non-zero entries are along the diagonal and then between particles that are connected in our system. It's symmetric, and that's because we have to conserve all these quantities. So the amount of force on particle A has to be equal and opposite to the force on particle B, and this gives us a symmetric system. It's diagonally dominant, which means that the entries along that diagonal are always bigger than the entries on the off diagonal, and in fact the row and column sums all sum to 0. So the values on the diagonal actually cancel out everything on the off diagonal. And the fact that the rows and columns sum to 0 tells you that K has 0 eigenvalues that correspond to translational modes. The matrix is positive semi-definite. And this is because the semi-definite comes out because the matrix is insensitive to rigid body modes, so both the translations I just mentioned, but also rotations. It can be expressed as the negative Jacobian of forces or the negative Hessian of energy. And mathematically, this looks like K is equal to the negative partial derivative of forces with respect to the degrees of freedom positions. It's also the negative derivative of our energy, eta, with respect to the positions I and j. And this last formula actually shows you that K encodes all of the interactions between two particles that are connected. And so there's no interaction between particles that this derivative is 0. So let's back up and think about how we actually calculate elastic forces in our soft body. So what we first do is we calculate a deformation gradient or a deformation function, which is dependent on world positions and rest positions. Then we compute a deformation gradient. So this is the gradient of our deformation function, and this is just dependent on the deformation function itself. Then we'll calculate a strain, which is dependent on the deformation gradient and is a metric for deformation. Then we calculate the stress, which is dependent on the strain, and I'll talk more about that in a minute. And then we can calculate an energy, which is dependent on both the stress and the strain. And finally, from the energy, we can calculate forces, which will just be in the negative gradient direction, because forces try and undo energy, remove energy. Okay, so let's look at deformation and its gradient. So we have some soft body here on the left, and then we have its deformed configuration on the right. And so there's some function x of u that takes points u and maps them to points on the right x of u. So we can actually express this function if we linearize around any point u0. We can say that x of u is equal to x of u0 plus some linear function f of u minus u0. And if we look at this function and we want to take its gradient, the derivative with respect to u, we get that that's just f, right? So the x of u0 doesn't depend on u, f times u0 doesn't depend on u. The only thing that depends on u is this f times u. It's important to note that this deformation gradient expresses everything we need to know in order to compute elastic forces. Because elastic forces don't depend on absolute positions. We don't need to know x of u0 to compute elastic forces. Everything we need to know is actually encapsulated in this deformation gradient f, which ends up being just 9 numbers. So let's talk about strain. Strain is a measure of deformation. As I mentioned in the first part of this course, it's dimensionless. It has no units, and that's really important. We don't want to be mucking up our measures of deformation with some notion of meters or scale or time or anything like that. It's a function of the deformation gradient. It's dependent only on the deformation gradient. Nothing else affects it. And there's 3 common strain metrics used in computer graphics. If you go back a decade or more, I guess it's more now, but if you go back more than a decade, you'll see that lots of people use the green strain metric, which is 1/2 F transpose F minus I. The nice thing about the green strain is that it's invariant to all rigid body modes. So rotations end up getting canceled out when we take this F transpose F. And that's really nice because we don't want elastic forces to penalize rotations. The disadvantage of green strain is that it's nonlinear, right? We have this F transpose F showing up, and that just makes things a little bit more complicated. It makes it so that we can't pre-compute as much stuff, and which makes things less efficient. It also, because it's nonlinear, things tend to grow faster and get unstable easier, and so it can be a little problematic. The second strain metric is Cauchy's infinitesimal strain metric. It's 1/2 F transpose plus F minus I. This is an approximation to green strain. So if you look in our course notes sometime later, you can actually see the derivation of Cauchy's infinitesimal strain. But the assumption is that the strain is very, very, very small. And it works very well in this context, actually. So Cauchy's infinitesimal strain is the underlies all of the theory behind modal analysis that's commonly used in engineering when you're building bridges or airplanes or things that you don't expect to, or you hope don't deform very much. But the problem with Cauchy's infinitesimal strain is that it's not invariant to rotations. We're not multiplying F transpose and F, and so we don't cancel out those rotations. And so if you have large rotations, you see huge distortions in your results. The most popular strain metric in computer graphics in the modern day is this co-rotated strain. And you'll notice that it looks a lot like Cauchy strain, except that we're using this F tilde instead of F directly. And F tilde we get by taking the polar decomposition of F, so F equals QF. And what we've done there is we've explicitly factored out the rotations. So to address this fact that Cauchy's strain metric is sensitive to rotations, we just figure out what the rotation is and remove it. And then we compute our strain based on the scale and shear that's left over after we remove the rotation. And as I said, that's the most popular approach in modern day computer graphics. Okay, so moving on from strain, we'll talk about stress. Stress is a function of strain. Stress actually does have units. It's a physical quantity. It's newtons per meter squared. And it models, the stress strain models are basically the material model. That's where you go from just measuring what the deformation was to telling what the stress in the actual system is. So this is your material model. These models can become extremely complicated. And especially when you're dealing with organic materials, the models are very, very complicated. And you can find entire textbooks that are this thick with different material models and then parameters for those models specified to particular materials. You can actually have an entire career in material science building these models and then fitting real-world materials to them. But we'll just focus here on linear stress-strain relationships. So in general, we can say that the stress is a linear function of the strain. Here, C is what we call a rank 4 tensor. You can imagine sort of like a 4-dimensional matrix. It has 81 coefficients in it. But it turns out that because both the stress and the strain are symmetric quantities, C ends up with just 36 real coefficients, or 36 independent coefficients. It turns out further, though, that if you assume an isotropic material, this boils down to just 2 coefficients. Here we've used the Lemay parameters lambda and mu, but there's actually lots of different ways to specify these 2 parameters. The Poisson's ratio and the Young's modulus, there's all sorts of ways, and you can look on Wikipedia. I think there's a table of like 6 different parameters and how they relate to each other. But here we've used the Lemay constants, and we say that the stress is just lambda times the trace of epsilon times I. So what the trace is doing is it's an approximation to the volume change. So you can sort of think of lambda as how resistant the material is to changes in volume. So if I push on it this way, how much is it going to expand this way? And then the second term is just 2 mu times epsilon. So this is just how much we resist deformation in general. And yeah, for an isotropic material, that's the only sort of parameters that you get. From there, we can specify our energy now that we have our stress and our strain. And in fact, it's just the product of the stress and the strain. This is the tensor product, which is a basic generalization of the dot product that you've seen in linear algebra. We just take each component of each tensor and multiply them together and sum them up. And then we can define the traction. The traction is a little bit of an unintuitive quantity. It's the force per unit area, and the area is the area that's sort of orthogonal to that normal direction n. We can define forces now. Given the energy, forces act to turn that internal elastic energy into kinetic energy. So they're in the negative gradient direction of that energy. So we take the gradient with respect to our degrees of freedom, xi, our positions, and that gives us what our forces are. We can also define forces as the integral over the boundary of some region of the stress times the normal. And this is actually in practice what people typically do because it's faster to compute. And then I'll just briefly mention plasticity. If you tend to SIGGRAPH papers, you'll see lots of different plasticity models. There's been a lot of active research in plasticity over the last few years, actually over the last 20 years even. The model the basic idea here is that we break our deformation gradient f up into two pieces. The elastic part, and that Fe, that'll determine what our elastic forces are, and this Fp, the plastic part. And Fp models the permanent deformation that's happened, usually because something has failed in the system. And this won't be undone. It's actually changing the rest shape. So Fp is modeling how the rest shape is changing based on this plastic deformation. And then I'll turn it back over to Tamar, who will tell you about fluids.
All right. So possibly the first thing you think about when you think of fluids is a liquid, but actually fluids also refers to gases. And here's a bunch of examples. So we see some different scales and different phenomena. We see some honey dripping on a spoon, a very large ocean, some crashing ocean waves with a bunch of spray and a breaking wave. And then we can see this also on a smaller scale, this lime with these air bubbles that are trapped there inside the water, possibly. This curling smoke and these big smokestacks releasing smoke into the air. So all of these are different fluid phenomena, different scales, but they're all fluids we might be interested in modeling in physics-based animation. So intuitively, a fluid, we could describe it as something that's going to take the shape of a container that it's in. And mathematically, fluids are usually described as materials that can't support shear stress. So here, I've taken this block of material, colored in blue here, and we're applying a shear stress to it. And what that means, the fact that it's a shear, means that it's tangential to the surface of this. Now imagine that this was some kind of block of rubber. If I shear it like that, you could imagine that the rubber, its internal forces are going to resist that. And you can imagine I could hold that for a while. I could hold that shear force, and the block will resist that with internal elastic forces, and it could stay stationary like that. So that means that that block can support a shear force. But a fluid can't do that. If I do that to a fluid, it's not going to be able to maintain its shape like that when I shear it, and it's going to start flowing. So that's really what characterizes a fluid mathematically. So though they can't support shear forces, fluids can actually support normal forces. That's what's happening here in this image where we have this balloon, inflated balloon. The elastic forces in the balloon are pushing on the fluid inside the balloon. In this case, the fluid is probably air or some gas. And the elastic forces are trying to compress that fluid. The fluid can support these compressive forces. What happens is that a pressure arises inside the fluid to push back on the balloon, and the balloon can maintain its shape like this. Okay. So in graphics, the equations that we're usually using to describe a fluid, because many of the fluids we're interested in are the incompressible fluids. So the equations that we're often using are the incompressible Navier-Stokes equations. So this looks a lot more complicated than F equals ma, but really it has a similar structure to F equals ma. So on the left-hand side here, m, the mass, we have a density instead. So the units of this equation are not force, but they're rather force density, force divided by volume. So instead of mass, we have density. Then we have an acceleration term, which looks significantly more complicated than an acceleration, and we'll discuss why it looks this way. And then on the right-hand side, we have all the forces that are acting on the fluid. And this is really the sort of material model of the fluid. The terms here we have are density, rho is density, u is the velocity field. So before we were talking about velocities of particles. Now that when we're talking about fluids, it's very common to talk about a velocity field. So we're talking about the velocity at a point in space rather than the velocity of some particle that's moving, a piece of fluid moving around. This term here is the negative pressure gradient. P is the pressure. Mu is the coefficient of viscosity, but generally called the viscosity. And this term is the viscous forces acting on the fluid, which we'll discuss more. And then F here is a catch-all for any other forces that we're going to include in our fluid. So first we'll look at why the acceleration takes this strange form in the fluid. This is called the material derivative. And the idea here is that we're starting with a velocity field. U is a function of position, and also it can be a function, and generally is, of time. So if I had an animation here, this velocity field would probably be undulating. You can imagine this is how a river is flowing, and these vectors are pointing in the direction that the flow is moving at any given time. So F equals ma, it really applies to a particle. So if you imagine a particle that's a little piece of fluid moving through the river, and that has velocity v sub p. So the acceleration is the time rate of change of that velocity. But the quantity we're tracking is not this particle, it's actually a velocity field. So if we want to know the velocity of the particle expressed in terms of our velocity field, it's going to be our velocity field evaluated at the position of the particle, x sub p. So that's what that second line is here, u of x of p. And now we want to take the time rate of change of that to get the acceleration of the particle. Now notice that this u has two terms which now depend on time. One term is just depending on time because it's this changing unsteady velocity field, and the other term depends on time because we're trying to follow a particle to get this particle's acceleration so we can apply F equals ma. So that means we have to take the total derivative with respect to time. We have to differentiate both pieces. If we differentiate the first piece, we first take du dx and apply the chain rule, dx dt. That's this second term here. And then we also differentiate u just with respect to time. That's actually this first term here. So this is really just our material derivative with mixing here lots of different notations. But this is a commonly used notation in fluid, u sub t for the partial derivative with respect to time. And then u dot grad u is just another notation for that second term we got from the chain rule. I also introduced yet another notation here, which is commonly used. This is a capital D, du dt, and that's a common symbol used for this material derivative. This material derivative has lots of different names, so I think material derivative is probably most common in graphics, but it's also called substantive derivative, particle derivative, I think something like derivative that's moving with the flow. Okay, so that tells us why that acceleration term looks like that. Now we'll look at the pressure forces. So in an incompressible fluid, the pressure forces are forces that will arise instantaneously to resist any compression or expansion of the fluid. So if you take this balloon and you try to squeeze it, increasing the compressive forces on the fluid inside, the pressure will get higher to counteract that. And if you look at the form of this, the gradient of some field points from in increasing direction of the function. So the minus gradient points in decreasing direction. And so as our intuition would tell us, if we have an area of high pressure, area of low pressure, the fluid will be driven from the area of high pressure to area of low pressure. This term represents viscous forces in the fluid. What viscous forces in a fluid are internal friction. I put a table here of viscosity values for different fluids. So the important thing here is kind of the relative values. You can see, for example, honey has a viscosity that's more than 3 orders of magnitude times water, and air has an even lower viscosity. So honey resists shearing motions inside of the fluid even more strongly than, say, water or air. Intuitively, we can think of this as the fluid is kind of flowing in layers. And the layers can have, the velocity is changing as you go through the layers, but viscosity tries to make those velocities equal. So viscosity is making the fluid drag on itself. Mathematically, this is being measured by the Laplacian, which is this differential operator here that takes second derivatives. We'll see it a little bit more later. And the Laplacian, intuitively, we can think of it as measuring the difference of a function from the average value of its neighbors. And so if there's some difference, the larger that difference is, the higher this viscous force will be to penalize that difference from neighbors, to try to make everything flow at the same rate. Or speed, sorry. Okay. When we have viscous forces, then we also have what are called no-slip boundary conditions at solid boundaries. So a viscous fluid, where it contacts a solid boundary, it will stick to the boundary. And so if that boundary is not moving, the fluid won't be moving directly adjacent to the boundary. And it'll cause drag on the rest of the fluid. So the classic experiment is this flow through a pipe. A pressure gradient forces the fluid through this pipe, and it's moving at its maximum velocity. But because of viscosity, the fluid at the wall is actually stationary, and viscosity slows everything down as you go to the wall, and it assumes this velocity profile with the fastest velocity in the middle of the pipe. So generally, wherever we have solid boundaries, we need some kind of boundary condition for the fluid, and in viscous fluids, that's often the no-slip boundary condition. Okay, and the final term here is this catch-all F for any other forces acting on the fluid. This could be, for example, this is where we put gravity, but we can also put other things in here. There are certain models of surface tension that put the surface tension force in here, into F. F can also capture other interaction forces of a fluid with other bodies. Another thing that sometimes is put into F would be what are called control forces. So in physics-based animation, often when we're animating fluid, we want to make it do something special. So the example that always comes to my mind are the horses galloping down the river in Lord of the Rings. And so I don't know exactly how they did that particular example, but one approach to doing control forces is to try to force the fluid to assume some target by putting forces into that F. Okay, so we've talked about the first equation, which is F equals ma, or it's a conservation of momentum for the fluid. The second equation really just came about from conservation of mass for the fluid. Before we saw conservation of mass, we actually derived it quickly, and it had this form. If the fluid is constant density, then that first term is 0, and we can also pull the density out of the second term, and it just reduces to this simple form, which is the divergence of the velocity field u is 0. Okay. So this is called the divergence-free condition. It holds for a fluid that's incompressible, that cannot be compressed, or that isn't compressing or expanding. And another way of saying it, if we integrate it and apply the divergence theorem, another way of saying it is that the net flow through any boundary has to be 0. If there's a net flow in, that would mean the fluid would have to compress in order to accommodate all the fluid. If there were a net flow out, the fluid would have to expand. And so the incompressibility condition says there's no net flow in or out. Numerically, when we discretize this, as I said, those control volumes can be arbitrary volumes, or they have to be. This has to hold for arbitrary volumes. when we discretize this on the grid, often the volume we pick is some grid cell and say that the net flow in each grid cell has to be 0 for the fluid to be incompressible. And it's actually the pressure that will enforce this condition. Okay, so I think we are back to you. How are we doing? Did you want to take a break?
What do you think? 20 minutes? Yeah, let's keep going.
Oh, okay. We're kind of where we thought we'd get 90 minutes, right?
Yeah. So
Okay, we could take a few more questions.
Oh, yeah, let's take questions. Good idea.
All right, we could take some more questions now. Yeah. Sure. Yes. So the question is, can I? I'm going to repeat the question because you didn't go up to the mic. So, can I explain the Laplacian again? And actually, I didn't explain it too much. If you're here a little later in the course, I'll show you what the Laplacian is. But it's in 2D. It's d squared u dx squared plus d squared y dy, d squared u dy squared. It'll be a lot easier for me to explain it when we get to that section because I'm going to illustrate how it gives you the average, difference with the neighbor average. Yeah. So I hope you'll be here for the rest of the course. You'll see that. If not, please check it out later online. Yeah. Other questions?
The question. In the beginning part, you showed a Houdini demo. Will that code and that Houdini scene file will also be available?
The code will be.
Okay.
I don't know how to save Houdini files. I'm just not that Houdini savvy.
Okay.
Question for Adam. You mentioned the co-rotated strain tensor. You had a matrix Q in there. I was just wondering if you could talk a little bit more about where that comes from.
Sure. Yeah, that's just the polar decomposition of F. So we take F, we do a polar decomposition, which breaks out your matrix into a rotational matrix and a scale shear, so a symmetric matrix. When you break out that rotation and then you just basically discard it, you're explicitly saying that my strain metric is no longer sensitive to rotations. And it works really, really well. It allows you to pre-compute. It allows you to do a lot of pre-computation. Not everything is pre-computable, but it makes things much, much more efficient. And because the strain tends to be sort of linear in the amount of shape deformation, you get something that's a little less likely to go unstable. I'm sorry, what was that? Yeah, absolutely. It handles pretty much everything. I sort of follow this stuff. I think it's pretty much what everybody's using, unless you're trying to do something complicated. So if you're trying to model an interesting material, so like I really want to model what skin is like, then you're going to use something much more sophisticated. But if you're just saying I've got some elastic jiggly bunny, then the co-rotated strain is probably what you're going to use.